Information technology has a tremendous impact on everyday life. It is changing how we work, how we play, how we travel, how we interact with others. Our world is based on information technology, even if we don't see it. The exponential increase in computing power over several decades has been driving this evolution, and it must continue to safeguard our standard of living and to improve our quality of life.
HIPEAC is a European-funded network of excellence gathering over 800 highly qualified researchers. It was created in 2004 with a threefold mission: to steer and to increase the European research in computing systems, to stimulate cooperation between industry and academia, and to create a visible and integrated community in Europe.
HIPEAC has developed a vision that starts from the grand societal challenges. It combines them with application trends like the evolution towards ubiquitous access, mobile computing, the development of applications providing high-quality virtual impressions, and the creation of massive computing centers.
We are trying to build supercomputers in 10 years from now that would be 1,000 times faster. The main constraint for producing this supercomputer is the power. In order to reduce the power, we need to use heterogeneous processor, accelerator based on FPGA or GPUs.
The HIPEAC vision also observes important business trends like the convergence of functionality on portable multimedia devices of various sizes and shapes, and the continuing trend towards services such as offered by cloud computing. However, future innovations in information technology will have to deal with the following challenges. 1. Hardware has become more flexible than software.
We always expect software to be more flexible than hardware. New digital hardware designs are tightly constrained by the software that we're going to run on them. For example, banks, supermarkets and airlines all use software which was architected decades ago, but their hardware is much newer. Today, in practice, new hardware is more flexible than software.
2. Power defines performance.
The power efficiency problem is perhaps best illustrated by the requirements of the mobile phone, which have to simultaneously deliver feature-rich applications in a small form factor on batteries. To achieve this, we have to continuously innovate and cut across software and architectural boundaries and optimize the architecture and circuit implementations.
3. Communication defines performance.
In order to provide the most efficient architecture within large-scale supercomputers, all components with strong added value are integrated to provide an ease of programming. It's not just all the processors that make a powerful solution, it is an integration of standard components in combination with a uniquely designed communication ASIC. So we do not burden programmers with data locality and transfers.
4. Application-specific integrated circuits are becoming unaffordable.
In the more advanced technology nodes, the cost of development of ASICs are rising dramatically. The reason is simply that you can integrate more and more functions on complex system on chips, and the cost for verification and validation is skyrocketing. We see more the trend towards ASSPs than pure ASICs.
5. Worst-case design for ASICs has become untenable.
Do you know that in the near future this kind of cameras can have a bad day and be not able to do high resolution? The cause for that is the mounting aging and variability problems, which will prevent us to do worst-case design.
6. Future systems will have to rely on unreliable components.
Future chips will have more wires and transistors available. But due to their extremely small size, they become less reliable. To cope with this, we experiment with many core processors that can seamlessly detect and avoid faulty cores, even when the chip is in full operation.
7. Time is relevant.
Our next generation of embedded products will be built around new technologies such as multi-cores and probably less reliable components. our customers call for real innovative solutions to satisfy the increasing performance requirements, the stringent hard real-time constraints, and, of course, the safety requirements.
8. Computing systems are continuously under attack.
Criminals go where the money is. So with all our electronic banking and credit card transactions, as well as storage of valuable data and privacy-sensitive information within the cloud, it is clear that computing systems are and always will be under attack.
9. Parallelism seems to be too complex for humans.
Programmers are always fighting to get their applications to work sequentially. Bothering them with parallelism would really make it too complex for the human brain. Yet parts of the code can already be automatically parallelized today by the compilers. And the programmers should actually only have to give hints to the compilers about parallelism to let modern compilers do an excellent job in parallelization.
10. One day, Moore's law will end.
Even if the Moore's law is slowing down, I expect that the integration will continue for at least the next 10 years. A new technology like 3D and fully depleted SOI will continue in the increase of performances and allow for heterogeneous integration.
The complexity of the systems we want to build and the complexity of all the design constraints are growing at such a rate that it is no longer possible for humans to manually design and optimize such systems. Therefore, we have to rely on advanced automated tools to help us.
This leads to the central creed of the HIPEAC vision. Keep it simple for humans and let the computer do the hard work.
This vision has profound consequences. First, it means that end users should not have to worry about technicalities. Secondly, it means that the majority of programmers should not be asked to write explicitly parallel programs, but instead they should use the most appropriate, high-level, domain-specific language for their application development. A minority of programmers should build the tools for those productivity programmers.
Similarly, hardware designers should use component-based hardware design methodology using basic components. Only a small group of architects will design and optimize the basic components. Naturally, systems built from these components will be heterogeneous for performance and power efficiency reasons.
Finally, system engineers should use an abstraction layer to combine software sources from different origins in a portable way. Below this abstraction layer, compilers, operating system, hypervisor will generate efficient and reliable code and map the application on heterogeneous and quickly changing hardware.
Computers, on the other hand, must take care of the tedious things like 1. Exploring the design space, 2. Generating the system architecture, 3. Parallelizing the applications, 4. Dynamically adapting the hardware and software to varying environmental conditions. The design of future computer systems will critically depend on the quality of the tools that are available to support human creativity. The HIPEAC vision also reminds us that one day the technology scaling will come to an end, and then we should be ready to continue advancing the computing systems domain in other ways. The HIPEAC vision states that programming should not become synonymous with parallel programming. Instead, we should simplify programming and use common concepts and knowledge. Hardware complexity should stay manageable by using component-based hardware design, naturally leading to heterogeneous systems. System integration should be simplified by decoupling hardware and software through an abstraction layer. There is a huge need for more intelligent and advanced tools to help us design and manage complex systems and ensure their safety. And finally, We should start preparing the post-Moore era.
We strongly believe that European industry and academia have everything they need in order to successfully tackle these challenges. The HIPEAC network is highly committed to help steering and coordinating these efforts.
Thinking about the future isn't about tomorrow, it is how we think today.